Lecture outline 9, and it's going to talk all about chemical bonding, and there's one driving principle for bonding, and that is that what's called the Octet Rule. Chemical bonding involves each atom gaining, losing, or sharing electrons to get the same valence electrons as the nearest noble gas. This is called the Octet Rule because noble gases, except for helium, have 8 valence electrons. So before we talk about bonding, in which we have atoms bonding together, let's just talk about the atoms themselves and what are called Lewis dot formulas. These display the valence electrons as dots around the chemical symbol. For example, if you have the chlorine atom from the periodic table is in group 17. We've talked about how it has 7 valence electrons, as do all the elements in group 17. So that means that there will be 7 dots, and we typically put these around the chemical symbol in pairs on the north, what we might call the north, south, east, and, well, since there's only 7, only 1 dot goes on one of the positions. And if you put the dots scattered randomly around the chlorine atom right now, that's okay, but we'll develop a process for this. Sodium atom, chemical symbol Na, it's in group 1, and group 1 has 1 valence electron. And it doesn't matter which side you put it on, or really where, though we will tend to put them on the north, south, west and east sides, I guess we would call them. Okay, so these are what are called Lewis dot formulas, and those are for atoms. Now, there are 2 types of bonds, and only 2 types of bonds in general chemistry. Those are ionic bonds and covalent bonds. Let's talk about ionic bonds first and define, and we've talked about this before too, but we need to talk about it some more. An ionic bond is the attraction between oppositely charged ions. Those are cations, which are positive, and anions, which are negative, in large numbers to form a solid called an ionic solid. And a reaction that we might imagine that forms an ionic solid and allows us to think about the movement of electrons as an ionic bond forms involves 2 sodium atoms and 1 chlorine molecule forming 2 formula units of sodium chloride solid. And if we were to do Lewis, what we call Lewis dot formulas for the atoms, as we just did, we have 1, we have 2 sodium atoms, and we have chlorine, which has a covalent bond. And for now, I'm going to draw all the electrons as dots so that we can kind of see them. So just like we did on the previous slide, here is one of the chlorines, and I'm going to draw the other chlorine in green. So you can see it's 7 electrons. The electrons are indistinguishable, though, because an electron is an electron is an electron. What we can see is that these 2 electrons will be shared. Now, as the 2 types of, so the atoms and the molecules become sodium chloride, what's going to happen is that the sodium becomes sodium plus, and so it's going to lose one of its electrons. And we might imagine that one of them goes to one of the chlorines, the other electron goes to the other chlorine. That's going to create 2 Na pluses and 2 Cl minuses. So let's see if we can keep this color coded here. So here's a Cl with all 7 of its original electrons plus 1 more electron to make it Cl minus. And then there's another Cl, which will be the green one. And again, we cannot tell these electrons apart, but as far as keeping track of them, we can imagine that each sodium gives up an electron to each of the chlorines to create 2 sodium plus ions and 2 chloride negative ions. And if we think about the electron configuration for sodium atom versus sodium ion, sodium atom, 1s2, 2s2, 2p6, 3s1, that's an S, is going to lose 1 electron, and in the n equals 3 level, where the valence electrons are, now it appears to have 0 valence electrons. But from another perspective, and this is the correct perspective, in fact, it still has 8 valence electrons in the n equals 2 level. So I'll write that over here, each of the sodiums, 1s2, 2s2, 2p6. Really, each sodium has 8 valence electrons. In n equals 2. And on the other hand, the chlorine, or the chloride in this case, you can clearly see that each one of them has 8 valence electrons. And this ionic bond will now form, because the ionic bond is the attraction between a positive and a negative ion. And we've talked about this before, but we might as well draw it again. So the ionic bond is the attraction between the oppositely charged ions. And we'll just draw that down there. In large numbers, and that's why we call the ionic solids formula units, because the large numbers of attractions are very much, we can think of them on a one-to-one basis as well, and the formula unit is the simplest formula for sodium chloride. I'm going to leave this one as a companion problem, and that is ionic bonds and how they meet the octet rule. Now, we're going to start a long section on covalent bonds. Covalent bonds are when 2 atoms share 1 or more pairs of electrons. Covalent bonds generally occur between 2 nonmetals. And covalent bonds generally, as we will see, let's talk about that later. We'll have plenty of time for that. But now let's think about the formation of a covalent bond, and we're going to think about the formation of a covalent bond for hydrogen. And we're going to talk about this curve, and this curve is a curve between energy and internuclear distance, and this is going to be for 2 hydrogen atoms. And so out here at large distance, we have 2 separate hydrogen atoms with no attraction. And truly, that'll be out here somewhere. And so here's our 2 hydrogen atoms. And so internuclear distance is going to be the distance between them. As they get closer and closer together, we are getting closer along to 0 along the internuclear distance axis. This energy, because it is energy of position, meaning set the positions of the 2 atoms, is going to be potential energy. And we have done potential energy, reaction energy diagrams before, and this is related, although something different. What we can see is that as we bring these 2 hydrogen atoms closer and closer, let me talk about this. So remember, positive energy is, in this case, is going to be repulsion, and negative energy is going to be attraction. So there we go, attraction and repulsion separated by the 0 line here. So, and what happens is, as the 2 hydrogen atoms are brought closer and closer together, there will be an increasing attraction between those 2 atoms. denoted by the fact that the two atoms are lowering their energy. Energy. Okay, so we're getting more and more attraction between them. This attraction is the attraction between the electrons on one atom and the nucleus on the other atom. So we're getting more and more attraction. And at some point, the attraction is maximized, and that is what's called the equilibrium bond length. So right here, and let me get on page here. So attraction is maximized. And that when the attraction between two hydrogen atoms is maximized, that is what's called the equilibrium bond length. And that is how we think of a covalent bond. And why covalent bonds form, it's because the two atoms are lowering their energy, much in the same way in physics, a ball will lower its energy by rolling down a hill. Okay, so attraction is maximized, so that is the bond length. And then as the two atoms get closer and closer together, at some point, each of the two nuclei start to feel each other, and the nuclei start to feel each other and create a repulsion. And so as they move closer and closer together, there is an increasing, let's say this, at first it's an increasing repulsion because it's getting, but we can think of it as a decrease in attraction before it truly becomes a repulsion. So I guess the best way to put it is that the two atoms are increasing their energy as they get closer. And then it becomes less attractive between them, and finally repulsive, or a repulsion between them. And what happens is, just like a ball rolling down a hill or between two hills, it can rock back and forth a little bit. As we know, atoms vibrate, and so there's going to be some rocking back and forth, but it will always settle around this lowest energy point. We can also see, as a side note, that the portion on the inside with that smaller internuclear distance is steeper, so it's going to tend to roll back faster there. And what happens is it will turn out to be much easier for the bond to break this way than for them to get closer and closer together. Okay? So, as we embark upon our study of covalent bonds, I want to ask the question, what is a covalent bond? A covalent bond is the distance of maximum, or the distance in which two atoms lower their energy the most, the distance at which two atoms reach their lowest potential energy, at that point, or when they participate in a covalent bond, there is attraction between the electrons in each atom for both nuclei. So there is an attraction between the electrons on each atom for both nuclei. And the term covalent is going to refer to this attraction. The electrons, or so both of the electrons in each bond, are or shared valence electrons. So the term covalent is going to be shared valence electrons. And by shared valence electrons, there are going to be shared valence electrons. So both electrons in the bond count for each atom's octet. Both electrons in each bond count for each atom's octet. And so, when I draw a H2, let's see this, we have two hydrogen atoms. When they form a covalent bond, they will have two shared electrons. These shared electrons will count for each of the hydrogen atoms, and therefore this one, hydrogen, now has, well, hydrogen, remember, wants the same valence electrons as helium, which has two valence electrons, and so it does have two. And the other hydrogen gets to count both of these electrons, and it has two. So both of these hydrogen atoms have satisfied the octet rule, which for hydrogen means it looks like helium. It's easier to see, I guess, if we do chlorine, a molecule of chlorine, and we'll do many of these. Satisfies the octet rule with 8 electrons each, and the two shared electrons help it add up to 8.